Hello, fellow problem solvers. So today we're going to be doing a problem from the USA Team Selection Test 2012, problem number 7. Phenomenal, cool, I like this geometry problem. It's nice in its own way. It inspired my coach to make a problem once. Now, I suggest you try this problem out for a minimum of half an hour, ideally an hour and a half, maybe even 2. They're not more than 3.5 hours, actually not more than 4 hours, because especially if you're like getting decently good in geometry, you're solving like those lower hanging fruits, and you want to attempt something like a G1 or something a bit stronger than a G1, great problem to try out, even for a long time. But not more than 4 hours again. Now, if you'd like to go along with us, draw the diagram and put your first ideas out on paper for the next 10 to 15 minutes, and now let's begin. So what do you see in this problem? For me, I see a lot of points. So first let's draw a diagram. And the first thing to do when you're drawing a diagram is to figure out, okay, point by point, a lot of points, let's draw them bit by bit. So what do I know for first? I know this is alpha half, as is the angle bisector. And so I can calculate all the angles. This is alpha half and alpha half. And if you didn't know this before, L is then the midpoint of the arc BC, which means we have that LB is LC, that's how we have it's the midpoint. And then LM is perpendicular to BC. And now from here, we're seeing like the next thing is this circle around MDA. Okay, so what are we going to do with that circle? Well, okay, I mean, it intersects these two sides at points P and Q. So, I mean, let's draw them first. So something like this. And then we have these points. They are called Q to P. And let's see now, what do we know from them? Let's calculate some angles. Chase some angles. So we have this angle over here is alpha half. We have this is alpha half, so D is the midpoint of the arc, what's it called, of the arc AQP of this circle. So that means if we're going to take the midpoint N, which is the next thing literally, the midpoint of PQ, we know that DN is perpendicular to PQ, which seems important because we're extending this here and then putting a perpendicular. Now, there's two ways we can go about the problem, and we're exploring it. And it is to solve it forwards or backwards. Backwards is saying, assuming the problem condition is true, what else is true? So again, forwards is saying, okay, point by point, what do I have, what do I have, what do I have, what do I have? And we're doing here a little bit of a combination. And I'm not going too into depth with every single one of these points. So now let's see first, like, what would we need if we call this point H? It looks like it's on the circle, but it could be a bad diagram. So we want to prove that ML is tangent to HMN, so that this here is tangent. If this were true, what would that mean? Pause for 5 minutes and figure that out. And the answer is, well, it would mean this angle would need to equal this angle right here, right? Because this was tangent, then we'd have the angle condition. That's one way to think about the tangency. What would we also have? Well, because this is a 90 and this is 90, remember, going at it step by step helps sometimes, and here it does. And so then this angle, so the angle HDL will be equal to HNM. In other words, we would have that DL and NM are parallel. And that is enough for us to prove. And mind you, what is this whole thing like? That is to prove that NM is parallel to the angle bisector. That's what's enough for us to prove, right? And what are we left with when we think about it in those terms? Well, we can forget about H. I mean, we can forget about L. We need either D or L, and we're left with proving that NM is parallel to AD, right? We've gotten rid of a point, and that's Generally useful in geometry if you can do so, if you can just get rid of a point by point, that can be helpful. Now let's pause you for 15 minutes, try to push this forward. We have a target, and I'm going to clear up the board and try to push it forward for the next 15 minutes. And now, boom. And now we have a new diagram. Now I want to draw P and Q carefully now. And what do we have here, mind you? We have, for P and Q, like how would I draw them? Like how without drawing a circle? Sort of like another way to think about P and Q. And for me, there's two really things that come to mind, though really one major one here. Is that, okay, this is alpha half, so this would be alpha half, and then I have the angle PMD is 180 minus alpha half, so this one will be alpha half. So one way is to take the angle alpha half, which is roughly this size, and draw it here. And then do the same thing on this side over here. And then we have boom, boom, we have the points P and Q. Okay. And this defines them uniquely, just this angle of alpha half. Okay, so we have all these alpha halves and halves nots. So we have alpha half here, and we have alpha half here and here, which says what? Well, it says that MP is now parallel to LC, and MQ is parallel to BL. We need to prove something. Things are parallel to each other here. A lot of things. And finally, we need to prove like LC, LB, MP, MQ, MN, LA. It seems like, there's like some sort of connection going on here, like, boom. Maybe there's something to this, maybe not. However, let's continue. So, if this is gamma, if this is beta. So let's now do some fact finding for P and Q. What do we know? And for me, one thing I would see is two ways to go about this. One way is to say, let me use power of point to sort of calculate what BQ is. What AQ is, like where is Q? So BQ is equal to BD times BM over what? Over BA. And on the other hand, I have CP is equal to CD times CN. These two things are the same, over CA. Now what is CD over CA and BD over BA? What's their relationship? They're equal. And so, mind you, this takes, I've prepared for this video, but also it's for experience that you begin to notice these stuff. You're like, okay, wait a second. BD, CD, BA, that smells like similarity, is it? I mean, that smells like equality, like the angle bisector theorem. And then you see, oh yeah, it is. And that's how you find out that then BQ is the same as CQ. And in fact, we could even explicitly calculate what it's equal to, though that may or may not be necessary at the moment. We know we can't do that. And now with that, we know that BQ and PC are the same. And we also know what? We know this by also the fact that if we just use the sine theorem, right, this here is going to be beta plus gamma half, and this here is gamma plus alpha half. They sum up to 180. You have the same thing opposite these sides, MC and MB. So the signs here would cancel out. You have alpha half. You need, by the sine theorem, to have PC and QBB equal. That's a different way of thinking about it. And now we take in this midpoint. And there are two sort of ways to go about it. One way we could go about is to draw the line through M parallel, intersect here at M prime, try to prove this is in fact the midpoint. A potential way. Another thing is to say, wait a second. This thing, like this is parallel to this, and this. I'm really I'm trying to prove that mn, like in this sort of triangle, like we have these parallel things. It seems like, but we don't have QPs parallel to BC. So it seems like maybe there could be something there, but not really. Now, one way is to go ahead and say, okay, wait a second. If NN is parallel to this is alpha half plus gamma. So we need this angle to be gamma and this angle to be beta. This is also a midpoint, mind you. So we would need, one way to think about it, is we know the sum of these angles. Actually, I only see this approach now. But we know the sum of these two angles, right? The sum of these angles is 180 minus alpha. We want them to show that these are beta and gamma. What's one way of doing that? Well, it's by a lemma we know from other problems that show that is, if I want to prove that x is equal to y, I can prove that sine of x over sine of alpha minus x is equal to sine of y over sine of alpha minus y. This implies x equals y. And now in here, that is to say, I want to find sine of the angle NMP over sine of the angle NMQ. I want to show that this is equal to, in fact, sine of the angle beta over sine of the angle gamma. Like, this is my question mark. If I prove this, I'm done by trigonometry. How can I prove this? Well, because this is the midpoint, I have from these two triangles applied the sine theorem there. I have that this, in fact, is equal to the sine of the angle. Well, so I have NMP, so that gives me sine of the angle QPM over sine of the angle PQM, I believe. Because I'll have sine of this is going to be equal this over this times the sine of this. So that's why I'm getting QPM up if I had NPM up. So now with this, what do I do? What is this? Well, this is really this side over this side, correct? So QPM, PQM, this is going to equal to QM over PM. Now what is this? Wait a second. So this is gamma alpha half. I already have alpha half and a gamma. So I have PM and QM through the elements of the triangle, right? And given I do, what does that mean? I can calculate what QM over PM is. And I can use the signs, or I can go ahead and say, okay, similarity-wise, what do I have? I have PN, PM over A D is equal to what? It's going to equal, well, let me put it on these two things, is equal to CN over CA. And now I have also QM. Again, I'll have AD will equal to what? So QM. I'll have AD. I'll take BM. Which gives me BA over BM. So now, what does this imply? Well, it implies that this QM over PM, actually I did this the opposite way, but what happens when I divide, actually when I multiply these and then flip them around, I'll get QM over PM is CA over BA, because the CM and BM cancel out, the ADs cancel out, and I get this is true. However, this thing right here is equal to this. But what is sine of beta over sine of gamma? Sine of beta, AC. Well, this is equal to AC over AB. And that's why these two things are equal. And then by our lemma, we get that this is equal to gamma, this is beta, and we're done. Now, this is not how I've done it, and there's other ways to go about it without trigonometry. Another way to go about this is to say, okay, wait a second, I have these two are equal. I want to show this is parallel to this, and I have a lot of midpoints. Now, how can I take advantage of the fact that I have these two things are equal? How can I connect them? And at the same time, take advantage of the fact that I have these midpoints, sort of to get some other angles. And one response to that question is to say, okay, can I make any sort of parallelograms? And if I do, where would I sort of transport these distances? Or not maybe parallelograms, maybe some midlines, because those give me distances that I can use. And one way to do that is to connect BP and say take the midpoint of BP, call this point, let's put it here, call this point T. Then Tn is half of QB and is parallel to QB. On the other hand, this is on this line, and then I can also take the midpoint of CQ, do the corresponding point here, call this point F. Okay? And then I have NF is parallel to this. Now also, MT is parallel to CP, right, on the other side, and it's half of CP. So this is parallel to this, which is parallel to this. This is parallel also to this. So I have NT is parallel to FM, TM is parallel to NF, is parallel to AC, and I have now all of these are not only parallel to each other, but all of these sides are equal to each other. So I have a what? A rhombus, correct. I have a rhombus here, which means what? Well, that means if we draw a rhombus, you'll see that if I do this, now because this is equal to this, I have this angle is x and this is x, and so is then this by the parallel condition and this. So in fact, we have NM is the angle bisector of this, of TMF. Now, what is TMF, the angle? Well, remember, TM is parallel to this, so we have this whole angle needs to be equal to what? This needs to be gamma, this needs to be beta, and this whole thing is then alpha. We can also get it from this is parallel to this parallel to this, this is parallel to this, then you have their intersections form the same angle of alpha. And now because this is the angle bisector of TMF, means this is alpha half, so I have this is alpha half plus gamma, which is what I needed. And that's another way to solve it. A third way to still go by this same route is to, literally the same route, but somewhat more creative, but I think I want to show this to you, is to say, okay, let me reflect P and Q opposite the midpoints of AC and BA. That'll give me a lot of midpoints to work with, but also it will help me use this condition. Like if I put this as a Q prime, this thing right here is P prime, I'll have this as perpendicular to this. I'm going to reflect them opposite these midpoints here. And now if I clear this up a bit, and once we clear this up, we get all of these midpoints, and this is a lot of midpoints. But what do we have from them? Well, we have this T prime here is a midpoint, this intersection of the angle bisector, so we need to prove that really AT prime is parallel to NM, or that this is NM is perpendicular to P prime Q prime. But what do we have from the parallelograms? Well, we have that N, T prime B1 and C1 is a parallelogram, which means what? It means a lot of things, but one thing it means is that n prime t prime halves b1 c1 and vice versa. But now what is also a parallelogram? Well, it is b1m, c1m, a. b1m, c, a. This is parallel to this is parallel to this. And so we have that am is also halves b1, c1. So all these three lines pass through the same point, and this point is the midpoint of all of these three line segments, which means that nt prime halves am, which means, and vice versa, and that means that nm t prime a is a parallelogram, and from there we have the problem statement, because from there we have nm is parallel to ad prime, which is parallel to ad, and we finish up the problem. Now, this is not the way I did the problem when I first solved it. My thinking was different, and let me show this to you. Going back to square one. So one of the goals with this channel is to show you different ways in which problems can be solved. Because one of the things that helps you solve problems better is this exposure to different solutions. Also trying it out yourself, but exposure does help. Now, an exposure to different ideas and different ways of thinking. Now, this was my thinking when I initially solved this. And that was okay. First things first, I have this ADM thing, right? The circle around it. What's another point that's just like killing me to like put it in? It's asking me to put it in. And the answer is, well, the midpoint of this upper arc, call this point, say S. Why? Because this is 90, this is 90. It gives me so many more conditions. And with P and Q, I sort of have now a mental image of ds is the diameter of the circle. And I can have a lot more fun with P and Q now. They're a lot more accessible to me. Now next is like once I have the P and Q points, and then this midpoint. Like I immediately put in S, and then I drew this and put the midpoint. Now, how do I put a midpoint? Well, I connected S and N, and then I saw, wait a second, D, N, and S seem to be kind of collinear. You know, that's my geometry sense saying, oh, I should probably look into that. And one of the ways to look into this is another background of theory that I have. I saw this pattern a lot when you have two circles and a line going through, like these two lines that goes through one of the intersections. And if I take this other point, I have two types of similarity. I have this triangle similar to this one, so this one is similar to this one, and also this one is similar to this one. And I can do a lot when I have similarity like that. In fact, if I take, say, the midpoints of these two, then also this triangle is similar to this one. And that's what I'm thinking in the back of my mind as I'm seeing this picture, as I'm seeing the diagram. Okay, I need to prove that. I prove immediately that BQ and CP are equal. And from there, I notice, okay, this is actually at 90. And now why are these collinear? Well, S is the midpoint, yes, of one arc, but it also needs to be the midpoint of the other arc because this is 90 minus alpha half. If you put it here, you'll get 90 minus alpha half alpha, so this must also be 90 minus alpha half. And then I know S and D are collinear. And then but then what happens to H? That initial thinking that H might be on the circle immediately gets solved because, wait a second, SL is the diameter. So I know that H definitely is on the circle. And now what do I need? Well, I need SM squared is SN times SH. It also gives me a nice way to prove this tangency condition through lengths. Like it's different, but it's also nice. And it gives me a way to prove it through lengths. And so I immediately go, wait a second, I have SM. Can I get SN? Or can I maybe get SN over SM? Like, what do I have? What do I need? That's the question I ask myself. Well, Sm over Sn, I have because Sqp and Sbc are similar. So I have Sn over Sm is going to equal to Sq over Sb, but also PQ over BC. And now what do I have? Oh, wait a second. PQ, BC. Can I connect it to something that's also similar? Like, mind you, I have alpha here and I have alpha there. So I can connect it to anything on this circle over anything on this circle. I mean, anything that corresponds to one another. And now what corresponds to one another? I'm using this term vaguely. But one thing that corresponds is the diameters. And diameter here, I know diameter of PQ is equal to SD, and diameter here is SL. Now, what do I need this to be equal to, right? What is the question mark? The question mark is if Sn over Sm is equal to Sm over Sh. Now, I need this. I have this is equal to this. Can I connect these two in any way, shape, or form? What would that imply? This is literally how I solved it. This would imply, wait, Sm times Sl, so that's Sm Sl, Sd Sh. Well, that would imply these four are concyclic. Oh, they're concyclic. And that's how I solved the problem. I did not think of the problem going at it backwards initially. It was just like, wait, this is just so cool. My sort of spidey sense is telling me that these three might be collinear. And then just like went through that. And then saw, oh, wait a second, these are concyclic. And we're done with that. But this is just like four different ways of solving the problem. Really two different approaches. One approach was really focused on this background knowledge that I had. And when I saw the circle immediately, wait, so let me put in this point. Why not? Why not put in that point? So that's like one approach. And the second approach was really just going at it really backwards until we saw something. Wait a second, this leaves out H completely. We don't have to think about where H is. If I just focus on NM parallel to AD, and it also looks like it simplifies the problem a lot. And you can also prove that, there's so many ways to finish up this problem. You can also prove through the similarity of S and M and SQB. I think almost 100%, I'm almost 100% sure you can do this, that you can prove, actually, I proved it. So we have this triangle similar to this triangle. Now, which angle do you have in these two triangles? Well, you have this angle. This is beta minus gamma half. And so that means this angle, SMN, is beta minus gamma half. And from here on out, I thought from here on out, it would be very, very simple. Oh, wait a second, I have SMP is something I already have. SMP is going to be 90 minus alpha half. So this is going to be beta half plus gamma half. And this here is alpha half. And so when you sum all of these up, actually this is 90 plus beta half minus gamma half. That gives you the angle we need. And that's a fifth way to go ahead and solve this problem. It's very, very cool. I really hope you tried it out. And I hope you learned something from this one. I think there's different approaches here. And as always, thanks for problem solving.